third talk of this session will be text comparison using soft cardinality. Sergio Jimenez, Fabio Gonzalez, and Alexander Gelbukh. Sergio, you present.
Okay, good morning. My name is Sergio Jimenez. This is work that has been made with Professor Fabio Gonzalez at the National University of Colombia, and also with my advisor, Alexander Gelbukh, from the SIG of the IPN here in Mexico. Well, this talk is about text comparison using soft cardinality. We use the term cardinality in the context of the cardinality of a set. The same concept of cardinality what we learned at the elementary school, with the idea that the cardinality of a set is the counting of the different elements in a set. So if we can remind those times when the teacher showed us a set with two repeated elements, if you want to convert it to a real set, you have to compress those pairs of identical elements into only one to be a proper set. Well, so we are trying to use the same idea for trying to make a different approach from, for instance, from fuzzy sets, to try to falsify that concept of cardinality in order to make approximate comparisons of text. Well, this is, we have two bags, and I wonder about that question. Can you make a better comparison between two bags, removing redundancy? Well, we are looking here two pairs of elements, of bags with different elements, but we want to, because we are in the task of comparing text, let's think each phase like a word, like a term, and each part of the faces, like the mouth or the glasses, as the alphabet. So, if we want to compare those pair of bags, it's quite tricky. I don't know how to say if they are similar or not. Look similar, but what happens if we try to compress, comparing at character level? So it starts to become maybe easier. I don't know, but now we can notice that the only difference was a pair of glasses and a beard. So we're using that intuition to compare text. Well, now let's compare the classic concept of cardinality with the proposed soft cardinality concept. In this bag, because it's not a set, we have two repeated penguins, we applied the knowledge that gave us our teacher at the elementary school, and we know that the cardinality of that set is 4 because the pair of identical penguins only counts once. Okay, no. Now the intuition in this other bag, considering a softened version of the cardinality, could be that not only identical elements could be must be compressed, but similar also must be compressed. So it doesn't work. Okay, this one is we need the same idea of the classic cardinality. Identical elements have to be compressed, but also similar ones. The two dots have some kind of intersection similarity, and the penguin with the glasses and the penguin without glasses also are similar. So in this scenario, we can think that the cardinality of that set is something like 2, but maybe 2 point something more. Wow. Let's try to define the concept, the idea of soft cardinality. If we have a set S with n elements, let's say, first of all, we will convert this set as another set with which elements are subsets, not elements, but sets composed with each one of the original elements of the original set. Now let's say that the cardinality, the normal cardinality of those sets is only 1, because with the idea that when we are counting cardinality, each element counts 1. And now, how to consider the overlapping between elements? Okay, in the case of the penguins, we could ask for instance, for human judgment, how similar are those pair of penguins? That judgment about if 2 elements are similar or not can be obtained using a similarity function. We normalize it between 0 and 1, which complains the triangular inequality and have all the normal properties of a measure or a metric. So what would be the soft cardinality of the original set? Let's think that it could be the union of those elements converted into sets with their intersections, but the total union. Well, let's try to use this slide to make the things clear. If we have a set with a tiger, a lion, and an elephant, first we convert this into a set of subsets in which each and next we have to take into account that we are considering each subset with a cardinality of 1. So in that image could be one could be think that it's the cardinality could be represented by the area. So let's think in circles of area 1. Now, try to assess the intersection between those sets with an external function that gives us a similarity, saying, for instance, that a tiger and a lion are more similar because it has a larger intersection, that the similarity between a tiger and an elephant or a lion and an elephant, and which could be the final soft cardinality of the original set. Okay, the idea use alpha to compute that similarity or those intersections. Finally, we are looking this, the area of the union of those sets composed by the elements of the original set. Wow. Now the problem is how to compute the cardinality of a list of sets, knowing that there are some intersection between them. Well, also from the elementary school, we know that the union of the cardinality of two sets can be obtained easily by making the addition of the cardinality of the individual sets and subtracting the intersection. Well, that's very easy for two sets. For 3 sets, it's more tricky. We have to add the cardinality of the individual of each set individually, then subtract pairs, the cardinality of the intersection of pairs, and adding the combination of 3, and so on with sets with more elements. We have first a problem. It is clear that the intersection between two sets or elements can be obtained with an alpha function, but a binary function. So how can we get a three-array function to get an idea of the size of this? So we have not too much three-array functions or for n-array similarity functions for a larger number of sets. Second problem is that for computing that cardinality of the union set, we have too much elements. Basically, to have 2 exponent n into 1, that is a huge number, where even for small numbers of n. And another problem or thing that we cannot ignore, because one is tend to try to ignore those terms, because the larger the number of sets that you're considering in this intersection, the size of the cardinality becomes lower. So those terms at this side become each time smaller. But if you know that the cardinality of pairwise intersection is large, this is also large the cardinality of the other numbers. So, for instance, in this example, there are 3 sets, and we know that those cardinalities are high, and we easily can see that the cardinality of the intersection of the 3 sets is also large. So, how can apply the idea of the soft cardinality with those limitations? So, the point is we have to approximate the computation of that definition of soft